The focus of this episode will be the use of mathematical operations in the context of a programming environment. Maybe you hate math, but it should be clear that in an environment like Max, data is represented with numbers. And specifically, this data refers to musical events or sound. For instance, a make note object can be used to construct a note. Arguments set a default loudness in the scale from 1 to 127 and the duration in milliseconds. The noteOut object sends out the note we constructed. We make the connections for pitch on the left, followed by velocity. The input for the make note is a value representing pitch. In this context, pitch, velocity, and duration are all represented by numerical values, which together create a piano note. And when there's values, we can do math, for instance, adding a value to the pitch to create an interval. Generally speaking, sound is represented by numbers or values, all deriving from mathematical procedures. To start simple, using a plus object with the argument 12, we realize adding 12 to any input. The number box from the outlet will display the result. The arrow up key on the keyboard is used to step through the values 1, 2, 3, which produce 13, 14 and 15 as results after the addition. Now let's try dividing by 16. However, it seems that producing values on the input always results in a 0. I don't see any change. Let's try inputting 16. The division seems to work properly, however, what we have realized is a whole number division. The output can be understood as showing how many times 16 fits in the value at the input. Another type of division is capable of showing fractional numbers as a result. The function is the same, what changes is the argument. It is written with a decimal point. As we have seen, the F key on the keyboard creates a so-called floating point number box, capable of providing and displaying floating point values. Now we can see the actual result of a division by 16. Now, returning to the previous version of division, although it may seem limited, in some cases a whole number or integer division can be useful. This becomes more clear with the modulo operator, which is created using the percentage sign. The result of modulo can be understood as the remainder after a division. In other words, 16 fits twice in 36 and the remainder is 4. A common conversion for which simple math is needed is between the Fahrenheit and Celsius scale. Wikipedia shows how that is done. Degrees Fahrenheit minus 32 multiplied with 5/9 results in degrees Celsius. It is best to create this conversion with floating point calculations. The value 5/9 can be calculated in a calculator application from where we can copy-paste it as an argument into a max object. 99.9 degrees Fahrenheit approximates body temperature. This realizes Fahrenheit to Celsius conversion. Looking once more at the multiplication with the factor 5/9, this could also be written as a division by the reciprocal, which is 1.8 and slightly more comfortable to type. Going the other way, we need to do the inverse. First multiplying with 1.8, then adding 32. Testing this with the value we see as a result at the left gives again 100, so this seems to be a correct implementation of Celsius to Fahrenheit. A slightly more challenging conversion is from MIDI note value or pitch to frequency. Again, Wikipedia gives a hint when searching for MIDI tuning standard. Here it says convert from MIDI to frequency. In order to realize this, we need to raise a value to a certain power with the pow object. The formula says that 2 becomes the base value. The input on the right is taken from a pitch value from which 69 is subtracted, the result of which is divided by 12. Make sure to define floating point arguments. The result of the power, according to the definition, needs to be multiplied with 440. Since the argument of the power changes, which is on the cold inlet, we need to trigger the base value in order to get result. It is fine to connect it like this. Testing this with the A above middle C, which is MIDI node number 69, it shows the result 440 Hz, which is correct. We can test for other values, middle C or 60, or the A an octave lower, which produces 220. This seems to be all fine. You may wonder why this is so, even when we have not defined a floating point argument for POW. It appears that the POW object is an exception from the general rule and always produces a floating point value, even when an integer value becomes the argument. Since a number box potentially can be confusing when it is about displaying numbers, I choose to print the value in order to see exactly what it is. And indeed, it is a floating point value. In the case of monitoring what exactly is produced from an object, it is possible to use the right inlet of a message, which sets what is displayed by that message. It is great we managed to implement this complex calculation, but actually it existed already in Max. There is an M2F or MIDI to frequency object which does exactly the same. Just to test, indeed we see the exact same results. In the case of such a complex conversion, rather than using a collection of objects, it is possible to write it as a single mathematical expression in a designated object EXPR. Let's start with a simple example. Variables that can be handed to the expression through inputs require a $sign notation. $sign I1 represents an integer coming from the first inlet to which 5 will be added. This seems to work fine. If we want a floating point division, we should use $sign F1 instead. Now, if we would implement MIDI to frequency conversion, we have to write the following formula. 440 times the power of, between brackets, 2, between brackets, $sign F1 minus 69 divided by 12. Let's test this. Great. The brackets in the expression are there either to enclose multiple arguments to a function, in the case of POW, or to force a certain order. First the subtraction, then the division, which otherwise would be done the other way around, following the rule that multiplying and dividing have higher priority than adding and subtracting. Sometimes we need to deal with lists of values, also referred to as vectors. In such a case, it would be useful to apply a mathematical function to each of the values. That can be done with VEXPR, a math expression for vectors. With a message as a monitor, we can see that this works just fine. Using the same function, we can express a division where the argument becomes a variable using $sign F2, which creates a second inlet. The result of this, however, is not a list of 3 values, but a single value, it appears. The reason is that the object will apply to each value of the list at the left inlet the function using a corresponding value from the second inlet. The length of the output is defined by the shortest list at the input. The expression doesn't know which argument to use for the other values. We could fix this by providing 3 arguments to the second inlet. In a case like this, it is also possible to set an attribute of the object, which controls specific behavior. Typing the add sign exposes two attributes that can be set. Also here autocompletion works. Scalar mode is an attribute that can be turned on with the value 1, of which the result is that a single value is used as a so-called scalar in this calculation for all values on the left. The result of a list of 3 on the left inlet is 3 values on the outlet. Earlier we have encountered the m2f function. This object is exceptional to the extent that it can do the conversion on a list of numbers. 3 values in, 3 values out. As we have seen, Wikipedia is a source of various mathematical expressions. One of my favorites is Julian day, which represents the continuous count of days since the beginning of the Julian period and is used primarily by astronomers and in software for easily calculating elapsed days between two events. We need to scroll a bit down to find the JDN or Julian day number. It would be great if we could just copy this and paste it into an expression object. It complains, however, of an error in the syntaxes. Certain characters are not allowed in an expression, but maybe we can clean this up in a text editor. My preferred one is Sublime Text, which allows to extend the selection with other matches. First of all, the multiplication character is wrong. Y, which stands for year, will become a variable, coming in through the first inlet as an integer. M, month, is an integer in the second inlet, and finally D, day, which occurs only once, the integer in the third inlet. It appears that not all dashes are the correct minus sign. That needs to be repaired as well. As a side note, the Wikipedia page mentions that divisions are integer divisions towards 0. This means division should not round off to the nearest. Well, this is exactly what we have seen Max doing when making integer divisions. Let's try to copy and paste this. That seems fine. No errors and 3 inlets. Let's test this with a known value. Here it gives an example. 24th of February 2023 was Julian Day 2,460,000. Let's provide that date. That seems to be fine. A year after this date, we see the count has gone up by 365. There are some mathematical expressions that are capable of exhibiting chaotic behavior. Turning to Wikipedia once more, this is the logistic map, the archetypal example of how complex chaotic behavior can arise from very simple, nonlinear dynamical equations. The logistic map is famous for producing this image. Let's implement it. The formula is quite simple to remember, but I'll use a tool to create a snapshot of it. Once it is copied, in Max we can choose Paste Picture. Again, using an expression, the value for R is going to be represented at the second inlet, and the value for X, N, at the third inlet. Note that the first inlet is not used in the mathematical expression. This is done with a reason that will become clear in a minute. The formula expresses that the next value, or xn plus 1, becomes something based on the current value of x, which is xn. Or a floating point value enters the third inlet, but that value is what just came out from the outlet. That is why we connect to both. The second inlet is the factor r, for instance 3.5. To the first inlet, which will trigger the evaluation, I will connect a button. Pressing the button doesn't give any result yet, because the input 0 for x will produce a result of 0. We need to initialize it to a different value, for instance 0.5. Now we see changing values at the outlet, at each trigger. Providing triggers can be done with the clock using Metro. Changing the factor r produces different behavior. However, it is much better to appreciate chaotic functions when we can make audible their inherent quality. A comparison generates a 0 or 1 whenever the statement is false or true. We see this happening when printing to the max window. The change object reduces the stream of zeros and ones by filtering out repetition, or change outputs whenever the input changes. Again, printing shows single occurrences of 1, each followed by a single 0. A select object, or cell, creates a trigger whenever a 1 occurs at the inlet. This can become the trigger for make note, creating a piano note number 75. In the MIDI standard, it is defined that channel 10 is for percussion sounds. Note out takes an argument for channel. Changing the value for R changes the rhythmical pattern that is generated. Take into account that the value for R should not become larger than 4, as it will run away towards infinity. Minus infinity in this case. When that happens, we need to reset the expression to a value between 0 and 1 and lower the value for R. In this episode, the differences between max and PD are not that many. There exists a make note object as well as note out. However, the fact that we heard piano notes from Max, and this applies to the Mac OS system, was because Max knew where to send these notes. PD doesn't, but it is possible to use, for instance, Reaper as a means to make them audible. This requires inter-application communication of MIDI, which on macOS is possible using the IAC driver that can be enabled through Audio MIDI setup. When it's about doing math in PD, an important difference is that PD does not distinguish between integer and float. Everything is float. It is possible, however, to do integer calculations using the expression object. The modulo operator produces whole number values as well. Finally, applying functions to a list of values is not an option in PD.